We're now going to look at section 2.2, which discusses regular graphs. So a regular graph is just a graph in which all of the vertices have the same degree. You could also talk about it in terms of being all graphs where the minimum degree is equal to the maximum degree. So some examples of regular graphs, cycles, every vertex has degree 2, so we would say C cycle is 2 regular. Complete graph of order n, every vertex has degree n minus 1, so it's n minus 1 regular. And our hypercubes of dimension n are also n regular. So we've already seen a number of regular graphs in our classes of graphs that we've looked at. We're now going to look at theorem 2.6, which basically tells us about the existence of regular graphs of particular order. So there exists an R regular graph of order n if and only if at least one of R and n is even. So what this means, if we think about the 4 different possibilities, R and n both being even, one being odd and one being even, and both being odd. This theorem is basically telling us that if they're both even, I should be able to find an R regular graph of order n. If R is even and n is odd, yes. R odd and n even, yes, that graph should exist. If they're both odd, that graph should not exist. So if we think about the 4th case, that would be easy to prove because if n and r are both odd, we would be trying to draw a graph where every vertex was odd or had odd degree and there were odd number of vertices. And we saw by the corollary to the degree sum formula that that graph cannot exist. So that for sure is out. So that leaves the other 3 possibilities. And what the proof of theorem 2.6 gives you is a method for constructing graphs that have these characteristics. So we don't need to show that every graph can work, we just need to show there exists. So if we give a method to construct an R regular graph of order n for each of these 3 cases, then that would be our proof. Now, what the proof actually does is it's going to take the first 2 cases and consolidate them into kind of a single case where R is even. So whether n is odd or even, the proof will be exactly the same. And then the second case where R is odd. So that's how the 2 cases are divided up. We're now going to go through an outline of the proof, starting with the case that R is even. And remember, n, it doesn't matter if n is even or odd for this particular case. So R, since it is even, can be written as 2 times some integer k, and 2k is going to be less than or equal to n minus 1, because that's our maximum degree in a simple graph. So here I'm going to deviate from the notation in the book a little bit. So in the book it says to label your vertices of the graph v1, v2 up to vn for our order n, just because I find it easier to explain. We're going to start at v0 and we're going to go up to vn minus 1. So we still have n vertices, they're just labeled slightly different. So we're going to arrange those around in a circle. So we'd have over here on the left-hand side, Vn minus 2, and so on. On the right-hand side, we'd have V1, V2, V3, and so on. So what I'll notice here is that on the right-hand side, I'm going to take that up to V sub k. And on the left-hand side, I'm going to go around kind of in this direction to V sub n minus k. And then somehow I have the rest of kind of my circle there. Now, because k satisfies this inequality that 2k is less than or equal to n minus 1, this set of vertices up to v sub k is completely distinct from this set up to going around this way to Vn minus k. There's no overlap. It could be that Vk is directly followed by Vn minus k, but they're definitely distinct, and there might be some other vertices kind of in between those two. And you could also see that you could say, okay, here I have k vertices. Over here I have k vertices. So this group plus this group is 2k. And I have this one, so I have 2k plus 1, but I can see that 2k plus 1 is less than or equal to n. So that's another way to convince yourself there's no overlap. So then what I want to do, once I have my vertices all laid out, I'll connect v0 to k, the first k vertices going clockwise. So there might be, a v3 there. And I keep doing that until I hit this vk. So that's what I do on the right-hand side. On the left-hand side, I'm going to do an edge to n minus 1, n minus 2, n minus 3, vn minus 3, up to vn minus k. And there might be some more vertices in between there. So it's going to keep going. So in total, I'm going to have, k neighbors to v0 over here. And I'm also going to have k neighbors for v0 over here. So in total, I have 2k. So that's what I would do with v0. Now I'm just going to rotate and do that exact same thing with v1. I'm going to say that v1 is going to be adjacent to the next k vertices around the circle. So if I'm going clockwise, v1 will be adjacent to v2, v3, v4, and so on, and I'd keep going, it's a dot, 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 and then I would go to vk plus 1, and then in the counterclockwise direction, I'll go to v0, which is already there, vn minus 1, vn minus 2, and then I would keep going until I hit the one, vn minus k. I guess it would be minus k plus 1. So again, just the first kind of k vertices after v1 in the clockwise direction, and the first k vertices to the left of v minus 1, kind of in this counterclockwise direction. And then I would just repeat that with every single vertex in the graph. And again, we're going to be retracing some edges over again. But when I'm done, every vertex will have these 2k edges and therefore a degree 2k at each vertex. So et cetera, we could keep doing that. Now let's just look at a particular example. Suppose we looked at something like n equals 7 and r equals 4. So if we use this, we have v0, v1, v2, v3, and so on up to v6. Now r equals 4, so that means k would be equal to 2. So v0 will be adjacent to v1 and v2, and then going around counterclockwise, I'd have v6 and v5. Now I'm going to look at v1. It will be adjacent to v2 and v3, so the next two in the clockwise, v0 and v6 counterclockwise. Now v2 clockwise, I'll get v3 and v4 as its neighbors. And counterclockwise, I want v1 and v0. That edge is already in there. So v2 is done. v3, you can see in the counterclockwise direction, that's already done. In the clockwise direction, I'll have v4 and v5. Now if I look at v4, the counterclockwise direction is done. The clockwise direction, I'll add in v5 and v6 from v4. And then finally at v5, the counterclockwise direction is done. In the clockwise direction, I want v6 and v0 is already there. and V6, there's nothing to do because all of the edges are there. So there's my, 4 regular graph of order 7. Now for the second case, which R is odd, again, we note that n must be even, and that comes from the corollary to our degree sum formula. We have to have an even number of vertices of odd degree. So if we want to look at this case, it has a very similar constructive proof to the previous one. So again, I'm going to deviate from the book a little bit and start at V0 and go up to Vn minus 1. Now, with this one, what we want to notice is that because n is even, with this particular notation, I can actually draw my vertices around a circle and have the vertex v sub n over 2 directly opposite v sub 0. Because n is even, n over 2 is an integer. Now, what I would do once I have this set up, I would put in the edges from the previous case. So I would go from V0 to V1, V2, up to ... to V sub k. So remember, there's going to be potentially more vertices in there, more connections. So I'm going to get kind of k neighbors here, just like I did in the previous proof. And then I'm going to also go counterclockwise, n minus 1, n minus 2, until I hit n minus k. So v sub n minus k. So I have another k neighbors here. And then I add one more edge to v sub n minus 1. So that's one more. So in this setup, my value r, r is odd. R is equal to 2k plus 1. So 2k will be an even number, so plus 1 more. So any odd number can always be written as 2 times an integer plus 1. And again, because R is in this range, this is always going to work. Obviously, if R is 0, I'm not going to put in any edges, but if R is at least 1, K would be 0, and I would just have that single edge opposite. If R equals 3, K would equal 1, and I have 1 and the 1 opposite, and so on. So I would do that at V0, K along here, K along this direction, and then the opposite. And then I would just repeat this for V1. I do K neighbors clockwise, K neighbors counterclockwise, and then I would look for V sub n over 2 plus 1 that would be directly across from it. So I would just repeat with every vertex in the graph. So let's look at the example where we have n equal 10 and r equals 7. So order 10. So I've labeled my vertices V0 through V9 and just arranged them around a circle here as evenly spaced as I could. We want r equal to 7. So 7 we can think of as 2 times 3 plus 1. So our k would equal 3 in this case. So with V0, we're going to connect that to V1, V2, and V3, and then V9, V8, and V7 counterclockwise, and then we connect V0 directly across to V5. Now we're going to repeat at V1. So V1, I'll do 3 in the clockwise direction, 3 in the counterclockwise, so I get V0 over again, V9, V8, and then directly across, V0 is across from V5, so V1 will be across from V6. And then I'll repeat this with V2. So V2, I'll go 3 back, so to V1 to V0, and then back to V9, and then 3 in the clockwise direction, 1, 2, 3, and then directly across will be V2 to V7. V3, I've already got the three edges in the counterclockwise, so I just need to work on the clockwise. So we will do those in blue. 1, 2, 3 in the clockwise, and then if I go directly across, I would be getting V3 to V8. Now at V4, again, I've got my three counterclockwise edges, so I need my three clockwise. So V4 will go to V5, V6, and V7, and then the directly across V4 to V9. So I'm always adding at my, for the directly across one, I'm adding half, so I'm adding 5. So 4 to 9 is 4 plus 5, so I'm adding half. And then now I can finish it off. V5, we've already got the three counterclockwise. We need the three clockwise. And I've already got the direct across to V0. So at this point, I'm always going to have the kind of across edges as well as the counterclockwise direction. So at V6, I'll just pick up the three clockwise around the circle, and at V7, I will pick up the three clockwise. 1, 2, and I've got the third clockwise already there. V8, I'll need to get to V9. And I've already got V10 and V1, so that finishes off. So there's the graph. And I should mention these are called Haywood graphs. And it just gives you a method and another big class of graphs to look at. So you can always generate a regular graph if you need an example of a regular graph of any order, as long as you're not violating that odd number of odd vertices rule that we have. All right, so that's it for section 2.2.